Note that in the building of our KNN model for prediction, which was a non-parametric model, we did not compute the closed form for the function f. Now we ask a question, how much more sales do we expect if we double the TV advertising budget? To do that with the KNN, we have to start with the original budget, double it, find the nearest neighbors, and then do the prediction. Another way of doing it is we build a model by first assuming a simple form for the function f. In this case, we'll assume a linear model. It has an intercept beta 0 and a slope beta 1. So fx will be beta 0 plus beta 1 times x. Then it follows that our estimate f hat will be equal to y hat, which is going to be equal to beta 0 hat plus beta 1 hat times x. The beta 0 and the beta 1 hats are the estimates of beta 0 and beta 1 that we compute using our observations. How do we do that? Well, let's start with some data. And now let's try one beta 0 and beta 1, one intercept, one slope. We get one line. Is that good enough? Well, let's try something else. Maybe this one is better, or another one. To decide which one of these models is the best, we can do the same we did with the KNN. We estimate the error for every model, for every beta 0 and beta 1, by looking at the residuals, the difference between the exact value of y and the predicted y. And we said the absolute value of the residual quantifies the error at each observation. And we, of course, want to aggregate all these errors, and we're going to use mean square error, MSE, for our loss function again. Now, in the case of linear regression, which we do now, the y hat has some explicit form. So we can now write the MSE to be y minus beta 0 plus beta 1x. And since we're using the loss function, we call it L of beta 0 and beta 1. Now we're going to choose beta 0 and beta 1 that minimizes the predictive errors made by our model, or minimize our loss function. The optimal values of the betas should be the minimum of the loss function with respect to beta 0 and beta 1. Now this procedure, this minimizing the loss function with respect to parameters, we call it fitting or training the model. Let's connect that to the sklearn that we've done in the exercise. First, we'll import the linear regression module from the sklearn linear model. They used pandas read CSV to read the data into a data frame, which we call DF. We use the TV column as X, and we use the sales column as Y. We use the linear regression module to instantiate the case reg. We use the reg.fit method, passing in the data X and Y to fit the model. Once this is done, we can use the coefficient attribute and intercept attribute to investigate our values, and we use the predict method to predict for any given X. Now let's look at that line, reg.fit xy. What happened here? We never explained what is happening there. We just said we're going to find the best beta 0 and beta 1. It seems to me that we're hiding a lot of things under the rug, and we should investigate and see what happened in the .fit method. In order to explain how sklearn actually finds what is the best beta 0 and beta 1, we should review some concepts. The first one is, what is a derivative? Well, the derivative is the slope when the limit of the difference between 2 points becomes 0. As you can see from the plot, the slope of 2 points, once the distance between them, the difference between them becomes very small, is defined as the derivative. Another concept we need to review is what is a partial derivative of a function. If we have a function, which you can see in the fancy machine we have here, that takes two inputs, x1 and x2, and outputs something, when we take the derivative with respect to one of the two variables, that is called the partial derivative. And this is defined as the rate of change of a function with respect to one variable while the other one is held fixed. Now, to do an optimization to find what is the best beta 0 and beta 1, that will happen when the partial derivative of the function will be equal to 0. There's three ways of doing that. One is brute force. That means we try every single value of beta 0 and beta 1 and evaluate the partial derivatives. We can solve these equations analytically. And the final one is to use a greedy algorithm, the gradient descent, something we'll see later in this course. Now for linear regression, we're going to try to do it analytically exactly. So we start with the loss function that depends on beta 0 and beta 1, and we want the partial derivatives with respect to beta 0 and beta 1. To do that, we need one more thing, which is called the chain rule. A chain rule tells me that if a function depends on another function that depends on a variable, the partial derivative of the original function with respect to the variable is the product of two partial derivatives. The first one is the partial derivative of the function with the intermediate function times the partial derivative of the intermediate function with respect to that variable. So if we think about our loss function, we can use that chain rule to derive the partial derivatives of the loss function with respect to beta 0 and the partial derivative of the loss function with respect to beta 1. Now after some algebra, I end up with two equations, each one the partial derivative with respect of beta 0 and the other one with respect to beta 1. I have two equations, two unknowns. I put it through my algebraic machine, and that will give me the values of beta 0 and beta 1, beta 0 hat and beta 0 1 hat, that minimizes the loss function. Now let's recap. We started with MSE, and the MSE is the average of the square of the residuals. In our case of linear regression, the estimate y, it's the linear function beta 0 plus beta 1x. We want to find the beta 0 and beta 1 that minimize the loss or minimize the error, or we call that fitting. We calculate the partial derivatives, we equate it to 0, we use algebra, and we find the values of beta 0 and beta 1 that minimizes the loss function. In other words, the partial derivatives would be 0. The line which uses the beta 0 and beta 1 is called the regression line. Now finding the exact solution only works for some rare cases. Linear regression is one of such rare cases.